Hello, my name is Burak Kantarci. I'm an associate professor at the University of Ottawa and the founding director of the Next Generation Communications and Computing Networks Research Lab at the University of Ottawa. Today I will be presenting our paper titled On Coalitional and Non-Coalitional Games in the Design of User Incentives for Dependable Mobile Crowdsensing Services. So let me briefly present the agenda of today's talk. I'll present a brief introduction of mobile crowdsensing, and I will introduce the dependability problem of mobile crowdsensing services, and I'll also talk about some of the existing game theoretic approach against dependability vulnerabilities in mobile crowdsensing. And then I will move to two existing game formulations that we had earlier proposed to ensure trustworthy mobile crowdsensing services. So this work will compare those two previous solutions because one of them relies on coalitions, whereas the other one does not have any coalitions between the participants. So those two will be compared in this case study, and I will be presenting you the simulation results. And then I'll make some conclusions as well as make some recommendations for potential future directions, opportunities, and talk about some challenges as well. Now, mobile crowdsensing is a non-dedicated sensing paradigm, which is a cloud-inspired model, and it takes advantage of the built-in sensors in smart mobile devices. So why do we need to take advantage of the mobile devices and their built-in sensors? Well, we would like to complement the existing dedicated sensing infrastructure to be able to collect information by taking advantage of mobile ubiquity of them. And that way we'll be able to leverage sensory data, and that sensory data will be able to contribute to some decision-making or decision support systems. So this is all good, but the problem or the challenge in mobile crowdsensing systems is the trustworthiness issue. So how can we trust a mobile crowdsensing based service? So there are several vulnerabilities here, and one of the vulnerability is, of course, the user privacy issue, and there have been several works that tackled the privacy issue in mobile crowdsensing. In addition to that, there's also the dependability issue, because we don't know who is joining these campaigns, and it's not possible to completely avoid having adversaries in the environment. So a malicious user may attempt to submit false sensing data, or another malicious user may submit a false sensing task, a fake sensing task. So these are different types of attacks, but they all affect the dependability of a mobile crowdsensing system. In today's talk, I will be focusing on the false sensing tasks, fake sensing tasks, and how to avoid those sensing tasks to ensure the trustworthiness of mobile crowdsensing based services. And to do so, I will be focusing more on the game formulations to improve the dependability of mobile crowdsensing services. But let me first start with the dependability of mobile crowdsensing services by focusing on the data trustworthiness issue. The first problem in the dependability of these services is a truthfulness problem. So why is truthfulness an issue? First of all, nothing is free here, so we do need to compensate or reward the participants by some means. So it can be either through monetary means or some gamification based rewarding can be considered. So it's out of scope in this talk, out of scope of this research. But what is important here to keep in mind is that the participants need to be incentivized. So we need effective incentives here. Well, It's good for the participants, but not everybody is going to be truthful. So the first problem here is the truthfulness problem. So we do need to compensate these participants at least as much as their sensing costs, but we don't know the actual sensing costs, so we just need to rely on what they report to the mobile crowd sensing platform. And if a participant reports significantly higher than the actual sensing cost, then this will lead to an unfair income increase from the standpoint of that participant. To avoid this, there had been an initial study, and this problem had been addressed. The second problem is the trustworthiness of the data. Now here, the motivation of the adversary or motivation of a malicious participant is not improving their income, but the motivation of the participant here is to cause disinformation at the mobile crowd sensing platform. So how do they cause disinformation? Well, by reporting false sensing data. So if we have an auction-based recruitment scheme for the participants, then these participants can join these auctions by reporting significantly low sensing costs to be able to be selected in these mobile crowd sensing campaigns. Well, here, to address this problem, we had earlier proposed a reputation-based selection or recruitment mechanism for the participants. So as long as a participant joins the campaigns and cooperates with the mobile crowd sensing platform, the reputation of the participant is ensured to be increased. So what do I mean by cooperating with the platform? Well, not publishing false data. So whenever the data is collected at the mobile crowd sensing platform, the data undergoes an outlier detection mechanism. And if a reported sensing data is marked as an outlier, well, that's a false reading. So a false reading will result in reduced reputation for that participant. So that was the main solution. And as you can see here, it just uses the statistics for every single participant. So this is actually a statistical assessment of the user reputations. And it is completely handled by the mobile crowd sensing platform. As an alternative, we can use a community-based recommendation system. So as you can see here, participants are considered as members of multiple communities in the monitored environment. So what do I mean by a community? If multiple participants have a common sensing task, that makes a connection between those participants. So they form a community. So if two participants have at least one common sensing task in an ongoing campaign, they are the members of the same community. As you can see here, a participant can be a member of multiple communities. But whenever a participant joins another community, every other member of that community is going to vote for the trustworthiness of that participant. And not everybody has the same vote capacity here in this setting. And not everybody has the same reputation level. And not everybody is going to cast a positive vote for this participant. So the reputation of this participant is going to be affected by the vote capacities of their voter and the votes cast by the members of the community, and of course, reputations of those voters. And as they join new communities, their reputation will be updated accordingly. So this approach actually adopts an existing Sybil detection algorithm that had been proposed for online social networks. So we had adopted this approach to implement a community-driven, collaborative reputation assessment mechanism for mobile crowd sensing systems. All right. So these two techniques were important, so that's why I wanted to elaborate on them, because they will be used in some parts of the game formulations down the road in this presentation. There are, of course, other techniques to address the dependability of mobile crowd sensing services. Well, one of the approach is reputation-aware sensor fusion, or another possible approach is using dynamic Bayesian networks, or we can use multi-agent systems, or another approach, as you can see here, is exploiting correlations. So by exploiting different types of correlations, the dependability of the data or the trustworthiness of the data is aimed to be guaranteed. So those different correlation types are like spatial correlation of sensed data and correlation of sensed data and the knowledge of provenance. Now, another possibility here is formulating some games between the participants, and also between the participants as well as the mobile crowd sensing platform. So I will be focusing on two previous schemes that we had earlier proposed. One of them is based on the coalitions, as you can see here. So this one leverages coalitions to ensure data trustworthiness. And this one formulates a repeated subgame, which does not form any coalitions in the environment. And we will be comparing their performance in a setting where adversaries occur. And let's start with the first one. So this is a repeated subgame for mobile crowd sensing trustworthiness. So in this work, we had formulated a repeated subgame perfect equilibrium-based approach. And this is formulated for collaborative decision-making. And the idea here is, if a user is being truthful, that user, that participant, is going to receive additional rewards. And that user will also have their reputation increased. And how does that work? Well, the recruitment of the users is partitioned into 3 stages, as you can see here. So we have a user recruitment phase, and we have a collaborative decision-making phase, and there is a badge rewarding phase. So here, the proposed solution is also coupled with a gamification approach as well. So this is where the awards are distributed among the users in the 3rd phase. This is based on their reputation. So how does this work? Let me get into the details of this. The first step, as I said, is the user recruitment phase. So here, the users are recruited based on the trustworthy sensing for crowd management scheme. So this was the statistical reputation assessment approach that I initially introduced in my talk. So once we recruit the users based on the statistical reputation approach, we save their initial reputation values, but we're not done yet. So in the next step, there's a collaborative decision-making phase. So here, every user has a strategy to vote or to not vote. And if a user is being voted by other users who report similar sensory readings for the same tasks, the vote capacity of that user is going to be increased. And if the vote capacity of that user increases, there's a possibility that the reputation of that user is going to increase as well. Now, how do we decide whether the reputation of the user is going to increase or not? Well, the vote capacity of that user, the new vote capacity of that user, is compared to a predetermined threshold. If the vote capacity is exceeding that threshold, the reputation of the user is going to be also increased. So we're going to be using the increased reputation value. Otherwise, we're going to stick with the initial reputation value that had been calculated by the statistical mechanism here. And in the former case, the user is going to be under the high award category. In the latter case, the user is going to be under the low award category. So the user is going to receive additional awards here. And if the user is in the low award category, the user is going to receive less award. And as we have new set of tasks, this process is going to continue. So here, we don't have any coalitions between the users. So we formulate a repeated subgame between the participating crowd and the mobile crowd sensing platform. The next approach does have coalitions. So a coalition game is formulated here. And it has 3 building blocks, as you can see in this slide. So the first building block, or the first step here, is the coalition formation game. And the second step is the winner coalition selection game. And the third step is the payoff allocation game. So the first step is to form the coalitions. The second step is for the users to select the coalitions to join. And the third step is to allocate payoffs to the coalition members of the coalitions. And as you can see here, let me just give a brief idea about the formations of the coalitions. As you can see here, we have 3 coalitions, and user 2 and user 5, these are the participants, to decide whether to join this coalition or that coalition. For user 2, there are 2 options here. User 2 can join either coalition 1 or 2, but there is a factor that this user uses to make their decision. And it is the influence factor. So the influence factor here is 0.7. In the second coalition, the influence factor is 0.5. So the user selects coalition 1, chooses to go with the first coalition. And from the standpoint of user 5, user 5 has 2 options, either coalition 2 or coalition 3. The influence factor here for coalition 2 is 0.5, whereas the influence factor for coalition 3 is 0.2. So user 5 will naturally go with the coalition that has the highest influence factor, which is coalition 2 in this case. So how does this work? The first step was, as you may remember, coalition formation. So here, for each coalition, a characteristic function exists, and that characteristic function maps every coalition to a payoff value for each user. And in the initial state, every participant is an independent actor here. So by being an independent actor, they are the non-cooperative agents in this environment, and they're the members of a one-person coalition. In the next steps, these coalitions are going to start merging, and they're going to start growing. So that's the coalition formation game. That was the coalition formation game. Now we have the winner coalition selection stage. Now here, every participant is going to look at the influence factors of the possible coalitions that they may join. And how do we formulate the influence factors of these coalitions? As you can see here, there are 2 main components of the influence factor of a coalition. The first component is the average trustworthiness score of that coalition, meaning the average of the trustworthiness values or the reputation of the members of that coalition. And the second one is the payoff indicator for that coalition. So these two contribute to the influence factor of that coalition. And the users are naturally to choose the coalition with the highest influence factor for them among the ones that are available. In the payoff allocation, there are two options to determine the payoff. The first one is the Shapley value, which is successful to ensure fair allocation of payoffs among the members of the coalition. But here, we are more interested in stability, actually, in this environment. So here we went with the core solution. So the core solution ensures that the summation of the payoff for all possible users in the subset of a coalition is at least as the value that each user would have received if they had opted out to participate individually instead of joining this coalition. So we do have the formulations in the paper for these payoff determination approach, but I just wanted to briefly summarize what they meant. So we evaluate the performance of these game formulations through simulations, and we have a Java-based simulation environment to perform these comparisons, and we monitor an area of 1 square kilometer where we have 1,000 participants, and every sensing task lasts for half an hour, and the sensing tasks arrive at a speed of 20 tasks to 100 tasks per minute. And we also have values associated to these tasks, which vary from 1 to 5, and also the sensing costs for the mobile users varies from 1 to 10, because the user recruitment in the initial step, which is based on the statistical reputation, remember, it actually uses the reverse auction mechanism that had existed in trustworthy sensing for crowd management. There are 3 possibilities for the malicious user population here. So the malicious user population can be 3% of the entire population, or 5%, or 7% of the entire population. So I'll be presenting you the results under each setting. But before that, it's actually useful to revisit our performance metrics. The first metric is the platform utility metric. So this is actually the difference between the values of the acquired sensing tasks and the rewards delivered to the users by the platform. So this is what we call the platform utility. The second metric is the user utility. And user utility is a similar metric, but this is calculated from the standpoint of the participants. So this is the difference between the received awards and the sensing costs. By sensing cost, I mean the bids that these users have reported to the platform at the beginning of these campaigns, and those bids represent their sensing costs. Of course, not every user is recruited continuously in every single campaign. That's why this value is averaged by the number of campaigns and also the number of winners. So this is actually the average user utility per mobile crowd sensing campaign. And we also have another performance metric, which is a disinformation ratio. Well, if we have adversaries in the environment or malicious users who report false sensing data, well, and if those users are being rewarded without being detected as malicious users, this is what we call disinformation. And that's another important performance indicator in this setting, because this one directly affects the dependability of mobile crowdsensing-based services. Now let's see the first performance results. As you can see here, user utility is evaluated under 3 different scenarios. In the first scenario, we have 3% of the population formed by these malicious users. In the second scenario, we have 5% of the population formed by these malicious users. And in the third scenario, we have 7% of the population formed by malicious users. And what we see in this figure is, well, if we go with the subgame perfect equilibrium based recruitment, which did not have coalitions, we can have at least 17% increase in terms of the user utility. And of course, we are not introducing additional computational overheads because we are not forming coalitions. We are not making any payoff allocation per coalition, or we are not introducing any additional overhead to form these coalitions. So with less computational overheads, user utility is increased at least by 17% when compared to the baseline solution, which is the collaborative reputation score approach. So this is the community-driven reputation score assessment. For platform utility, so we have a similar performance results here. What we can see, what we can observe here is, as the malicious population grows towards 5% and 7%, the subgame perfect equilibrium based participant recruitment outperforms the coalitional approach. And this is significant in this performance results. And how about disinformation? And as you may remember, disinformation occurs if malicious users are being rewarded, if they are being paid by the platform when they report false sensing data. Now, what we can observe here is, if we go with the SP-based approach, which did not have any coalitions, as you may remember, well, the malicious users can be eliminated, and also the rewards made to the malicious users are almost negligible, because these malicious participants are detected during the collaborative voting stage. So we can take care of the disinformation issue. We can take care of the user utility problem that the coalitional approach may face, and we can also improve platform utility if we go with the SP-based approach. And this is actually the conclusion that can be made out of this case study, this comparative study. So we have taken a closer look at potential game theoretic approach and game formulations in general for mobile crowd sensing systems. And we focused on 2 approaches here. One of them was using a repeated subgame, which did not have any coalitions, and the other one was forming coalitions between the participants. And what we saw here is, okay, both approach, they can improve user utilities under greater malicious participant population, but the improvement is not really remarkable. But the platform utility, we saw it can be significantly improved. And in addition to that, the disinformation probability is significantly reduced by the SP-based approach, where we did not have any coalitions. But of course, there are several other open issues, challenges, and opportunities for the researchers who work in this field. The first one is the investigation of the impact of the physical constraints in the wireless medium during the participants' recruitment. How can we consider them in this game formulation. And the other one is the vocational privacy for the mobile crowdsensing participants. How can we address it from a game theoretic point of view? And also we need to assure desired levels of service quality for the end users, not the participants, but the end users of this mobile crowdsensing services. And we can also introduce some game formulations at the end users platform to address some other dependability issues, such as elimination of the fake tasks, as I was mentioning at the beginning of this talk. And this concludes my talk on this topic. I hope you enjoyed it. Thank you very much.